All right, hello everyone. Thanks for joining me on this special lecture topic on the multiplexing. So I've done a good bit of research into this topic to prepare for this presentation. I have to admit I have not covered nearly everything. As previously Dr. Russ and even Jared have talked about, there's just a lot that there's to say about multiplexing. I did my best to cover as much of it as possible, but I kind of ran out of time. I covered a lot in analog. So a lot of what we learned in class was just focused on the digital aspect, specifically the gate technology that's used to make these. But there's really a lot more, especially analog side. Multiplexing is such a huge part of today's transmission protocols. It's wireless through coax cable or even fiber optics. So without further ado, I'm going to go ahead and get started with the PowerPoint. So I titled my presentation, The Perplexing World of Multiplexing. So before we go and begin, I kind of wanted to create an understanding of exactly what multiplexing is and why we use it. So I really like this quote here. This is a method by which multiple analog or digital signals are combined into one signal over a shared medium. But then the main purpose, the aim, is to share a scarce resource. So before multiplexing, we didn't have many ways to combine signals. The great thing about multiplexing is that there's so many different ways to combine multiple data streams into one single line to share a scarce resource. Like I said, whether this is through a single coax cable, through a single fiber optic line, whether it's even just sending radio waves through the air, where you can combine them out of a single antenna, out of a single data stream, then you can save resources, and it's much more efficient, and you can stream data faster. So multiplexing has really increased the data speeds in so many ways. It's really the reason that we can have internet and TV as fast as we do. So this, if you go online, a lot of times this is your broad outline of what you'll see for the types of multiplexers. So a lot of times we divide them up into analog and digital signals. The problem with this is that that's almost we put time division multiplexing, is what we've talked about in class, under the digital section of this chart. However, time division is really such a broad term that you can use time division in a lot of analog signals. So as we'll talk about soon, TDM is not a only digital process. This is used a lot of times for analog, and that's actually why I chose multiplexing as my topic, because I wanted to multiplex some analog signals that would be coming from sensors and then send those through a transmitter. This transmitter has one data stream, and so I wanted to multiplex these multiple analog signals and then send them through the transmitter. To do this, the only way I could was to do time division. So you split it up, and we'll talk about this soon. But anyway, so that's kind of why I chose this topic. It's very fascinating. So the general layout typically is you have your time division, and then you have your synchronous and asynchronous time division multiplexing. And then under analog, at least for this chart, they only have frequency division and then wavelength division. However, after much more research, there are many more, and these aren't even all of them. But as you can see here, I have placed this additional analog signal multiplexing underneath the TDM scope. And we'll get into this more, but like I said, the reasoning being is that you can time divide analog signals into the multiplexer. And then my second envelope is the analog division multiplexing, which this specifically, it does not use digital signals. This is like frequency division, wavelength division, polarization. This is spatial division multiplexing, and also orbital angular momentum multiplexing, which we kind of talked about a little bit last class, and I still don't fully understand everything about it, but I will do my best to kind of share. I spent a lot of time looking into these. So a bit of history regarding time division, or regarding multiplexing in general, but specifically, it started out in the time domain, and in time division. So as Dr. Russ was talking about back in the day when we had the transatlantic underwater cable, this is how we were able to transmit data much faster. A bit before this, a guy by the name of Emile Badeau developed multiplexing telegraph. So he was, there used to be, it was just a telegraph with Morse code. it was a very basic transmission. However, he had the idea to create one of the early bit encoding. So he encoded the alphabet with a 5 and a 6-bit. He later transitioned to a 6-bit encoding of the alphabet. So you can see here, so we have 5 bits, and so this is true, and the rest are false for A, and then so on. So he's encoded the alphabet into a 5-bit system, and then he created this telegraph type keyboard. This almost looks like piano keys here, that operators would punch the keys to correspond with the letters. So then you've got multiple signals that then were multiplexed and then transmitted through the telegraph cable. This sped up transmission times considerably. I think it was, they were able to average over 30 words a minute. I don't have the exact numbers, but it was much faster. Yeah, 30 words per minute, which is much faster than previously able with just a standard telegraph transmission. So this is one of the early ideas of multiplexing. And then after that, it really improved and continued to get better. And then eventually we transitioned to even other types of multiplexing. So here's the standard gate or the gate array that we've seen in class. We're going to start off looking at digital signal multiplexing. So the idea behind these is that we're taking purely digital signals, so zeros or ones, and then using gates, purely digital gates, to combine using AND to get our output to multiplex. So as we've talked about, these are our select lines, and based on the combination of select, it will enable one of our data transmission lines to go through the OR gate. So only one is transmitted at a time with this gate logic, and I will get into what this means and why this can change. So with digital signal multiplexing, you have really two different main types. You have synchronous and asynchronous. So synchronous is great. You've got fixed slot intervals for each line and device. So I want to kind of go ahead and talk about this a bit more. So here are 3 devices. They are each transmitting a signal at the same speed, the same rate. And so our multiplexer is going to scan each one of these in a sequence. So I have this oriented a little bit differently, but for instance, our select lines are scanning through each of our channels. As this video here is showing, the multiplexer scans each channel and then transmits it linearly through time. So a frame can be defined as a set of all channels accessing the multiplexer. So a frame includes the green, the red, and the blue. So one bit from each serial. So the nice thing about synchronous is that it doesn't require an address. On the demultiplexing side, you know what the sequence in the frame is going to be based on the predetermined logic on the front end. So you know that you expect first a green pulse, then a red pulse, then a blue pulse, and you can decode it that way. So there doesn't have to be any special addressing. It's always the fixed time interval. That's the key. You have a fixed time interval and you have a fixed sequence. Always one, then the other, and then the other at the same sequence in time interval. However, what happens if, for instance, this computer on the red line does not have data in its buffer, in the line? It's empty. So in that case, it would just transmit nothing. Then you would have an empty slot, as you would say. So this really slows down. If you're trying to multiplex multiple lines and a certain line is a slower speed line, you will have less data and your multiplexing will be less effective. So typically, in addition, typically these are implemented using CMOS gate logic. As I said, in these, there we go. These gates typically nowadays use CMOS. I know we talk a lot about TTL, transistor logic, but that is really kind of gone in the past. It's not used much anymore. I did a lot of research into this because I was a bit confused, when I was looking at the speeds about CMOS versus TTL versus FET. But really, CMOS is the standard today for gates, and as we'll look at here in a second, for just straight analog signal multiplexing. So moving on to asynchronous. So here's an example of what's advantageous about asynchronous. So for example, like I said, okay, these are our 5 computers now. So let's look at this picture here. So in this example, we've got 5 computers. So there's buffers on each one of these. So that this one has multiple A's in this case lined up, ready for the multiplexer to transmit. So in this case, let's go down here. Let's look at synchronous. Well, we can look here. What would happen is it would first shoot. It would scan the A, then the B, then the C, then the D. Send the frame. Then it would do another scan. Scan an A, B, but then we're on the second row now. There's no C. So now this slot in the frame is empty. So there's no data transmitted then. So this is a lost efficiency in our multiplexing. Once again, once we get to the 3rd row, then we don't have a B or a C. Under the 4th frame, then all we have is an A. So this is lost efficiency in our transmission. However, over here to the asynchronous, what happens is it only looks for data in a slot where there is data already in the buffer ready to send. So it will pass by slots that don't have any data. So in this case, our first frame grabs an A from line 1, doesn't grab anything from line 2, grabs a C from line 3, nothing from line 4, and then E from line 5. You see this, A1, C3, and E5. Goes to the next frame, A1, C3, E5, A1, C3, E5, and so on. Now, once it gets down here, and there's no more C's or E's, it'll just fill it up with A's until the sequence is done. So in this case, our frames are full of data. There is no loss efficiency. We're using the multiplexing, the line, whatever type of line we're using to send our data, at its max capacity. We can't send data any faster as it comes to the logic. Now, obviously, there comes to things about the data speeds of the lines, but so on. So that's great and everything. And this sounds like, whoa, why don't we just use asynchronous all the time? However, we have to think about on the demultiplexing side. So now that we've received the data, how do we know what data we've received? As I said, in synchronous, we know what the sequence is going to be. However, in this case, we might have an A, we might get something from slot 1 and slot 2, and then we might skip to slot 5. Demultiplexing does not know what it's going to be receiving. And so in that case, you have to address the bits. And so that additional address space can really add up a lot. So you're gonna be sending addressing bits in front of each byte behind that. Now, one way to kind of get around this is sometimes each frame will have the line of addresses sent in front of it to tell. But generally, the only way asynchronous is more efficient is if you have slots that are large. So basically saying you send a lot of data per individual slot. So that way the addressing byte that it takes or bits that it takes up is made up for the fact that your slot that you're sending behind it is a large data slot. And so your efficiency then counteracts the fact that you have to address each line that you're sending. So I found that really fascinating. I couldn't really find details about which ones are still used the most nowadays. But asynchronous versus synchronous, I think we've got a good understanding on that now. And like I said, these down here are just additional examples of how asynchronous can be beneficial. So getting on to analog signal multiplexing. So this is really, like I said, fascinating topic. I was trying to figure out how to implement this myself. I wanted to build a circuit, and it's a lot more complicated than it seems. There are chips. There's actually a chip on Spark Key that you can buy that multiplex analog signals. You've got your 0 to VCC voltage of range that you can send of a analog signal, and it will send it and multiplex it. However, there aren't really any internal circuit diagrams of how this chip works. So I did a lot of research, and generally, so the idea is there's these CMOS logic pairing kind of switches, they call them, are pretty popular to use. You know, transistors are great for switching. And in fact, even in the digital gates, the transistors are used in those gates for a sort of an effect of a switch. But this is a This is a very common circuit diagram of a paired CMOS switch. So we use the P-type and the N-type transistor in a pair here. And so how it works is this is our digital input, and these inputs have to be referenced. Transistors are very tricky, and I found this out when trying to do simulations, of making sure all your voltages are referenced correctly with regard to your gate, your source, and your emitter. But essentially, you're going to have to not, because the PMOS operates off of a zero or a low voltage in reference to your high, and then an NMOS operates off of a high in reference to a high in your gate. Basically, you want a high in your gate for the NMOS and a low in the gate for the PMOS. So anyway, this circuit here will then switch. When you put a digital high, it will allow your source to flow through the transistors and out the drain. And so this is a standard circuit. So moving away then, CMOS analog multiplexing is great, and it's pretty great. It shows less error. However, it can be a bit slow. I've also got this down here. This kind of shows. So kind of getting into, so transistors have an R-on resistance, kind of just an effective resistance of the transistors. And so I keep losing my mouse. When we're flowing voltage, our voltage of our source, as it goes up, we end up having this resistance of each type of transistor. So having these paired allows us to get a combination of the P channel and the N channel, to where we're here in the center, we can send a wide range of source signals through, such as sinusoidal, any type of analog signal. I think I'm going to go ahead and, well, okay. So I built circuits, and we'll get to that in 1 second. So the FET transistor, or the FET multiplexer, is the second main type that I could find. So these are really interesting. My mouse keeps disappearing. All right, there we go. I didn't find many examples. However, I did find a chip from TI that was just this. It said it was a FET multiplexer. So these are really interesting. Supposedly, they use a single FET transistor per line. So you have your analog signal going in, your voltage at the gate. As long as you have your correct drain resistor here to get the right current flow. These work as effectively switches to switch on each one of your lines, depending on what your select line is ready for. So one of the great things about FETs is that they're really fast, and we'll get into that more in speed on one of the slides later. But the speed is much better. Normally, you can find high-speed CMOS multiplexers. You can find low speed. It's just such a large range, as Dr. Russ was saying before. You can make general like comparisons, but really you can't give any specific numbers, because there are just so many levels of technology within the chip, and how hard they try to make it a fast chip, and the fast chips are obviously much more expensive. So I built, Dakota helped some on this too. I want to give him some credit here. He got together. So I had a little bit of a start on, let me get my source straight. Okay, so hope you can see everything. So this here is our JFET or FET multiplexer. So what we're going to do here is we've got 2 select lines. So this is a four line multiplexer, and this line here is simply a enable line. But we've got our 5-volt logic here, logic source. And these switches here I had to do in Circuit Lab, enable to get a transition in the select line. So I'll show you the simulation results here in a second. But this basically just switches through a combination of our outputs. So it'll select sine signal first, then triangle, and sawtooth, and square. So these are our input signals. We simply send them into the emitter of I'm getting my terms mixed up. Well, anyway, I'm sending it into the JFET transistor here. And where's my mouse? There it is. And then so when we have a high on the gate of the transistor, then it allows that signal to pass through. So these once again, like I said, transistors are finicky. I thought I knew enough about them after microelectronics, but played around with some resistance values, finally able to get that reference voltage correct, where you get that flow. Also, these diodes here are needed because with the JFET, you can get current sourcing back into the gate, which is really strange. Finally figured that out. So anyway, based on your select line, it will enable the transistor to allow the flow of current through it, which will then allow the signal flow. And so effectively what you have is you have a time divided analog multiplexers. Once again, these are time division multiplexers. So over here is the CMOS, the P-N type pair. This once again works the same way. You've got to knot it into the P type and it's high into the N type. And then once again, it just allows the flow, same type of switching network here. There are, now in Circuit Lab, I couldn't get the speed, the propagation delays to actually show. So I'm going to go ahead and head over to my simulation. So once again, same simulation. I'm just going to go ahead and run a time domain on that. I actually had already ran it before. I didn't need to do this. Maybe we can do that. There we go. Okay. So, all right. So here, so for the first couple hundred microseconds, I had line 1 enabled. So we have our sine signal. As soon as line 1 goes low, we have our triangle signal, and then line 2 goes high. And then we move on to a square wave and then our triangle wave. We've got this little drop here. I don't really know what that's doing, but like I said, transistors can be weird. Also, this is probably a feature of Circuit Lab simulation. Had a lot of trouble with Circuit Lab. It's a bit finicky. Sometimes I literally ran the same transient run twice and got different results both times. I don't know how I feel about this software. Okay, so there's the JFET. Works pretty smoothly. Just have to get these feedback resistors right, and it works. Then we're going to run. So this one, I went ahead and plotted our not our select lines, but our actual data lines that go into the gates of each transistor. As you can see, A0 through A3. So we got A0 through A3 here. So I'll go ahead and actually I've already ran it. So we're just going to open it up. So there we go, same thing. So we got our sine signal, triangle, square, and then sawtooth. So this again, this is A0 is high, and we got A1 high. As I guess it's A3, so we haven't flipped, and then A2. So yeah, it worked well. Only after like a whole day of figuring it out, but I got it to work. So I'm pretty proud of it. So yeah, theoretically this should work now. I'll pull this back up. As you can see, my voltage. Here, I was running from 1 volt to 3 volts on my analog in. This can get finicky if you have varying amplitudes reference to each other, especially if it's running into your 5 volt gate voltage. So ideally, I need a higher gate voltage to be able to get my correct voltage reference. But you know, all gate voltage is only 5 volts because it's logic. I would need some type of amplifying network to get that figured out. But hopefully I could implement this in real life with my circuit that I'm wanting to build someday and get that data multiplexed. All right, so I think that's all for that. On the next slide. Okay, so multiplexing speeds. So what I found in general from some data sheets, the biggest, and Dr. Rose talked about the sum. I got confused initially, but it's important to make a distinction between propagation delay between your data in and your data out, and then also your propagation delay from the select to your data out. Because what can happen is if you select a line, but then you're sending multiple bits through that, there's a propagation. Even as you're just sending data streaming through the transistors, there's a propagation delay. That is the main propagation delay you want to look at, because really most of the time the data is going to be flowing. You want to change your select as little as possible, because the select delays are really what's the largest. So in this case, for the FET transistor, we've got about a 0.35 nanosecond propagation delay, which theoretically, if that's your only constraint on speed, not including whether it's your coax or your fiber optic, if that's limiting your speed any, you could theoretically, with this multiplex, have a max speed of 2.8 gigabits per second. And with the CMOS, generally you're looking at 10 to 30 nanoseconds. And in that case, you're only 30 megabits. However, I found a specialized CMOS that supposedly had a 60 peak, or like I said here, specialized a 60 picosecond propagation delay, and that was for a CMOS. So like I said, there's really a huge variability. However, I did want to show this. I found this really old article that did a study into CMOS versus JFET in multiplexing. So this is actually in a multiplexer setup. So this is the settling time, and so curve 2 is this lower one, and you can see we've got more like strain attenuation here, and then the curve 1, which is our JFET, the settling time is much better and a much flatter response overall. So the takeaway from that was that the JFET was really a great tool for analog and multiplexing. So looking down here, I just kind of want to show you the difference again. So like I said, so this is between, so if you make the select choice, if you see your select line, you say I want this line, how long does it take for that decision to propagate through your logic to then control the correct output line? So in this case, the TPHL is the time from select to the output to. So it depends on your logic, but then in this case for your for the TPLH, sorry, this is TPHZ here, which is this time. This is supposed to say, oh, TPHL, there we go, TPHL here. That's on the back end. So from the end of your output to the end of your input to the end of your output is the delay there. A lot of different numbers, and it's really cool to look at these data sheets. Really a lot to learn from them. So I'm going to put some links at the end if you'd like to look at. Okay, we're moving along now. All right. I'm backwards here. We're going to move on to this slide. Okay, so moving out of time division, moving strictly into frequency domain multiplexing. So the idea of this is that you can encode bits of data upon a carrier frequency. So this can be in radio broadcasting, or it can even be in just coax cable. If you take a signal and then code it upon a certain frequency, then on your demultiplexing side, you can search for only signals that contain that certain frequency. So you can essentially fill up the spectrum of frequencies with signals. So in this case, like I said, so we've got signal 1, 2, and 3 signals. And now what you're going to do is you're going to assign each signal a certain frequency band. So in this case, maybe this was like 10 to 50 hertz. Maybe this was 1,000 hertz to 2,000 hertz, and this is like 15,000 to 20,000 hertz. So now you send that data all at the same time. So it can be, it's basically, it's parallel in the frequency domain, but it's simultaneous. Well, sorry, yeah, I guess parallel in the time domain, and series in the frequency domain. I think in this right, yeah. So you're sending it series regarding the frequency. So you can receive the data all at the same time, and you're using up, like I said, your sources such as the frequency domain to send the signal. So typically in the demultiplexing side, you use a local oscillator to produce the correct frequency to then cancel out that carrier frequency to then receive your data. So in this case here, this kind of shows what you would have. So typically your carrier frequency is much much higher than your baseband. So your baseband would be actual data that you're sending. So in this case, this is a local high. This is a single bit, single high, and you've encoded that onto this really high frequency signal. And I have done this in, you guessed it, Circuit Lab. Okay, so what I did here is I took we're gonna go back here, a square wave signal at 10 hertz. So that's our data. And I have placed it upon a 500 hertz, much smaller amplitude sine wave. So I've multiplexed this upon a signal. And so now we're going to see, so kind of think of this here as our output of the multiplexer, and then this over here is our demultiplexer. So when I simulate this, I'm going to look at what I receive on the output of the mux and the input to the demux, or actually I guess this is the output of the demultiplier, demux. I'm getting really tongue-tied. Anyway, let's go and run that simulation. Okay, so the blue line here is our multiplex signal. So what we've done is we've taken this frequency, like I said, you saw in that other picture, and we've transposed our actual data line onto this certain frequency pattern. And now, so I guess the brown, don't know what color that is our original signal, V-sig here. That you can see that kind of right back here. And so then this is our multiplex signal, the blue, and now the yellow here is on the demultiplex side. So this is the after it removes it. Don't know what the problem is with this attenuation. Didn't have time to figure that out. I'm guessing it has something to do with the diodes and the resistors, but I don't know why the amplitude of this is smaller. I simply just, so I did a phase shift. So just to cancel out the signal, we're going to do 180 degrees phase shift on this exact matching sinusoidal signal with these diodes to keep the current from flowing back. So I don't know what I did wrong there, but it shows the idea. So let's head on out of here. Back. Okay, I think we're doing all right on time. So wavelength division multiplexing. This is pretty equivalent to frequency division. I mean, if you know anything about light and frequency and wavelength is simply a proportional to wavelength is proportional to frequency by 1 over its speed of light over 2 pi, something like that. So what's the difference? It's really, you're measuring the same thing. It's just the inverse of the other in a way. However, we simply use this terminology to describe when you're multiplexing light. So in frequency division, typically that's referring to actual radio waves or even electrical signals. However, this would refer to strictly light, especially when it's applied to fiber optic cable. So this is done in a very similar way. You're simply using different wavelengths of light to multiplex your actual data line onto. And then you can transmit all that data in parallel on a single fiber optic cable. So like I said, you've got different data lines, and these are different colors of light. Theoretically, this is infrared. You're in high frequencies. I think we're talking like 1400 nanometers. The range varies, and then it's multiplexed on a single line. So your demultiplexing is typically done using a device called a talon. Honestly, I don't know how to pronounce that. This is really, so this is this picture here. They're optical cavity from 2 parallel reflecting surfaces. And then the waves basically can pass through only when they're in resonance with it, such as there's a certain wavelength. So fiber optic has a much larger bandwidth than coax, and I reckon I didn't finish this PowerPoint. So the speeds can get pretty high with fiber optic. In fact, there was a couple years ago, they got up to 2.6 petabytes per second, I think, which was using some, I never got a clear answer on it, whether they were just using multi-core fiber optic cables with spatial multiplexing, which we're gonna get into. I need to get moving. All right. Okay, this slide is a mess. Wow, okay, so spatial dimension multiplexing. So the idea of this is that you're transmitting data in parallel across space, not frequency, not wavelength, not time. You're using simply physical space. And so this is kind of typically the way the situation where this is kind of typically thought of as in phased array antennas. So this is kind of an example here. So you're using your space. You're taking one signal and then you're spreading it out across space and sending it in a parallel fashion, so that your receiver uses that space dimension to determine which signal is which. I think that's the best I can describe that. Interesting. All these things are, some of them are used together. Basically, any way that we can transmit data using different physical phenomenon as a means to encode that data is basically the whole method. So the other is polarization multiplexing. So this here is you're really referring to electromagnetic radiation. I have my picture cover this up. So this is where you polarize signals. So you basically, I don't know if you have heard of dual pol radar. So in that case, you're not sending data, you're just bouncing off of clouds and rain. But anyway, you use this axis to flip your waves into an orthogonal pattern here, and you can double your transmission rate by using this projection. However, in fiber optics, when you're using light, you can also do a circular polarization. So this gets into more electromagnetics, but with the electromagnetic spectrum, you can have a circular polarization of the actual light, and so you can use the direction of that polarization. You can use right-hand or left-handed polarization, and then encode data on each of those specifically polarized directions. And this here, it's careful to not get this confused with orbital angular momentum, because this uses light and this does use the this like helical pattern. However, it's not strictly polarization. And so let's get on to it. Orbital angular momentum multiplexing. So there's a bit of a, I don't know if you call it disagreement right now. This is still pretty new, but a lot of people try to frame this as a, as a quantum type new discovery, simply because it has to do with light and you're talking about angular momentum. And you do, now part of the reason this can be kind of true is because you do have topological charge states. So this is kind of a term used in quantum, where you add those individual defined states of like a quantum level, and that they can even go up to infinity. So in this way, this kind of is similar. However, most see it as really just a special form of our spatial dimension multiplexing, and not really a new quantum type of multiplexing, just because it really, as we'll kind of see here, it is not quite quantum in nature. So really the way this is multiplexed is that it depends on the spatial distribution of the optical field. So a light beam carrying a OAM possesses a helical wavefront. So as we see here, we've got these different wavefronts of light, and these can be created in a number of different ways. I read a couple papers on how they can create these. And so that can be described by, first of all, you have your axial position of the wavefront. So this is like, you kind of have to look at this as past in the time. So this is moving through space in time, and this is just tracing out the pattern. So this is actually your wavefront on the front end here for each one of these patterns. And so it can be described by its angle, and then also the topological charge as an unbound integer. So these are our integers of different types of helical patterns, but then also types of distribution of intensity. So this is your intensity distribution as well, and then this just kind of shows you where your how the time pattern flows behind it. So like in this case, you only have one helix, and this is kind of like a double helix, and this is a single circular pattern. So basically, you can use these almost infinite number of combinations to encode data on each one of these. So each one of these types can be encoded with a certain data set. And so this has got huge potential. It's still kind of being worked out. There's a lot of problems with it. I don't have time to go into all of those, but with transmission lengths, getting that transmitted over a longer just physical distance. And then also there's some problems with noise, and then also demultiplexing on the DMUX side. There's been some trouble, especially once you get on beyond like these basic five states that are the most common. So these aren't just, these actually do exist. I saw in the physical world, like they actually exist naturally. They were reading some of these signals in the helixal orbital momentum patterns coming from some far off galaxy. Just this little side note. And then this is Okay, I totally missed the slide. Remember that slide I skipped way back there? I forgot about it. So back to, if you can stay with me, don't get lost. We've got the frequency division multiplexing. Before that, there's a special type of frequency division multiplexing called orthogonal frequency division multiplexing. So FDM, the biggest disadvantage is that in the domain, so there's actually a spectral domain that the United States so-and-so organization sells certain spectral domains of that domain to organizations. I mean, there was a sale a couple years ago to Verizon for a large bandwidth of data. So these companies are then allowed to use that data line to send information across. Anyway, the problem with this is that each band or band set has to be divided from the others by a guard band. So that guard band helps isolate each set from the other bands. So that way, say I'm going to use the 900 megahertz band, but I've got a 2 megahertz guard band on either side. That way, my signals don't accidentally interfere with somebody's 905 megahertz signal, and so on. So with orthogonal, the idea is to remove those guard bands, to be able to utilize more of the frequency domain. So the way this is done actually is by transmitting your data not at a single frequency, but at multiple frequencies. So for example, if you have a set of data, you will use multiple frequencies and send them in parallel. So these bits will be sent in parallel in the frequency domain, not in the spatial or the time, but in the frequency domain. And so what you end up with is you have multiple peaks for each one of your data bits. And now the special thing about these is that they are all orthogonally placed next to each other. So you think in geometry, orthogonal is like a line that's perpendicular to the other. However, in signals and systems, this is actually where you end up having you have minimums at the other nodes, local maximums. So they end up canceling with each other. This is just a very the system works together really well that way. Everything is very pattern-like anyway. So you know what you're expecting on the demultiplexing side. You expect every frequency line to be exactly orthogonal to the other. And so there's less noise. And like I said, so you can send your data in parallel through that frequency spectrum. And you're able to eliminate the need for the guard bands. So a lot more into that. Still out. I don't fully understand. It's pretty complicated. So between this and the optical angular momentum, these two are really interesting, and there's a lot of in-depth reading you can do, and I'll have a few links at the end. This has also become pretty popular in wireless communication recently, to be able to enable more higher rates of communication using less of your frequency bandwidth. So this can cut down by limiting those guard bands. You can use up much more of your associated bandwidth. So say Verizon is able to send a lot more data on their, say, 10 kilohertz bandwidth than they were before. All right, well, that's about it. I had this extra little picture on here about OM multiplexing, but like I said, you've got your different helical structures here. In a sense, they're physical, but they're not really physical. Well, the best we can do is try to draw pictures of them. Then you have them multiplex together in a single set, and then that is demultiplex. This whole paper was about a new way to demultiplex, because like I said, that's one of the big challenges. And they had made some pretty big advancements in the past year. This is out of a group out of Japan, I think. So that's about all. I've got a few links here. This is not all of them. I will put some more on and I will get this posted, but I hope you enjoyed it, and just let me know if you have any questions, anything I can help with. But I think that's about all. All right.